Good afternoon, everyone. I want to welcome you to my lecture today. Of course, today we got two materials to work on. We first going to start with normal approximation to the binomial distribution. Then we also going to work on application of central limit theorem. And of course, the two documents we want to work on, they are more or less related because the central limit theorem we started the other time talk about the convergence of a probability distribution to normal. Okay, so let's get started. I want to start with this material. Of course, I've already uploaded this material. Okay, of course, I actually told you the other time the significance of normal distribution. Okay, so I think if I want to go historical, the normal distribution was actually discovered by somebody that I'm actually respect, De Moivre in 1733. De Moivre in 1733 was trying to see how he can actually use normal approximation for binomial distribution. Initially, the random variable was actually binomial, which means there are two possible outcomes. And he realized that you have a sufficiently large sample, okay, uh, the the distribution of the random variable actually converge to normal. Let me tell you, using the idea of central limit theorem, okay, we say that the sample mean or even the sum of a random variable, not only sample mean, the sum of a random variable will follow a particular distribution that is non-normal. The sample mean of a random variable will follow a particular distribution that is non-normal. But when we have a sufficiently large sample, of course, uh, they will be normally distributed. Now, so this was according to De Moivre in 1733. But let me tell you, in 1783, um, Laplace used the normal distribution to analyze errors, the measurement of errors. And finally, in 1809, I think somebody called Gauss, and that's why uh, normal distribution is also called Gaussian distribution because Gauss in 1809 used normal distribution to study astronomical data. So, but we want to focus on normal approximation to binomial. Now, let's take a look at a practical question. A candidate believes that at least 50% of voters support him, okay? To test his claim, okay, n equal to 100 voters are randomly selected. Among them, 45 support the candidates. Now, I need you to take a look at this. This candidate actually believe at least 50%, actually mean greater or equal. Does that make sense? So that is a belief. That's an hypothetical statement. And you know what? Let me tell you, investigation always follow a claim because that particular political candidate actually made a claim. And how can we validate his claim? Then the investigation will follow a claim. And that was why we randomly select 100 voters. And out of the 100 voters, 45 support the candidate. Now, mathematically speaking, we're going to say the claim is not right. But using this information alone, we cannot say the claim is not right. Okay? Because we need to be able to investigate statistically. Mathematical reasoning is different from statistical reasoning. The two numbers may not be the same mathematically, but in statistics, what we are interested is statistical significant difference. Even though there could be a mathematical difference between 5 and 6, but a statistical significant difference may not occur between 5 and 6. Does that make sense? Okay, now, if the true proportion of voters supporting the candidate is denoted by P, that's a population proportion, and it's indeed 50%, what is the probability that 45 or less voters in 100 randomly selected voters supporting? Now, we want to see here whether the central limit theorem is going to play out. You know, whether it's either when you choose a respondent at random, it's either the respondent support this guy or not, which make it binomial because it has two possible outcomes. So the distribution initially is actually binomial, but we can actually see whether the central limit theorem is going to apply. How am I going to know? The only way to know is to look at the threshold. What is the threshold? How large is it large? At least story. If you can see here, how many sample size do we choose? We actually choose 100. We have met the threshold to apply central limit theorem because the sample size here is at least story. You can see 100. Okay, now in answering the question, the experiment is equivalent to 100 independent Bernoulli trials. Okay, 100, because why is it called 100 independent Bernoulli trials? Because each person has two possible outcomes. It's either they say they support him or not. And when the numbers of trials in Bernoulli is more than one, we don't talk about Bernoulli anymore. We talk about binomial. Does that make sense? Okay, now take a look at this guy. Okay, we let I to be equal to 1 to 200, and where y high can be either 1 or 0, 1 if the voter actually supports the candidate, equal to 0 when they don't support. And you know what? The underlying distribution, we already know the underlying distribution for each voter is actually Bernoulli. Okay, take a look at this. Now we're using the properties of Bernoulli now. Okay, the y1, y2 up to y100 identically and independently distributed Bernoulli with parameter p. And of course, we know the mean of Bernoulli. Expected value of yi is going to be p, whether the expected value of y1 or the expected value of y2 or expected value of y100 is actually going to be p. And of course, the variance of yi is p multiplied by 1 minus p. That's property of a Bernoulli distribution. But take a look at this. You know, we want to sum the numbers of ones. What does 1 represent? 1 represents the response that's, oh, I support him. I know some they're going to say 0. Some will be 0. 0 means I don't support him. Then I want to add the numbers of ones. Okay, that's going to be in a sample of 100. Then I'm going to have a random variable t now, which is equal to sum of y1 plus y2 up to y100. And in the situation where y1, where individual is Bernoulli, then the sum of the Bernoulli is actually going to be binomial. So which means if y is a random variable that follow Bernoulli, then t is going to be a random variable that follow binomial. Does that make sense? Okay, now what is going to happen now? We're now going to have a random variable t that follow binomial. And what is the parameter for binomial? It's actually going to be n comma p. Okay, n comma p, where n is going to be the sample size and p is the probability of the characteristics of interest. And that was why you see 100 comma p. Okay, now they told us that assuming 50%, Okay, assuming 50%, we're actually assuming P to be 0.5. That's a population P to be 0.5. Okay, now we need to figure out P cap. The true value of proportion is P without a heart. Then the one with an heart, take a look at this one, is going to be a P cap, which we call an estimate of P, or can say estimator for P. Now, the estimator for P, I told you the other time, a P cap is the same thing as Y bar. Now, what I'm going to do there is just to do, what is it? T. T is the sum, right? Sum divided by 100, that's going to be the mean, right? The mean is the same thing as P hat. Any question on that? Okay, now, what we now want to do now, because of the fact that P cap is an estimator is a random variable because it was computed from the function of random variable that makes it random, that we need to be able to know what is the expected value of P cap. Oh my God. I know the expected value of Y. Y follow Bernoulli. Expected value of Y equal to P. But then if I want to know the expected value of P cap, then I need to be able to know the expected value of Y bar. Don't forget P cap equal to Y bar, right? And I told you the other time, if expected value of Y equal to a particular parameter, the expected value of Y bar is also going to be the same. So which means expected value of P cap is going to be the same thing as expected value of Y bar, which is going to be P. Does that make sense? So take a look at that. Because I told you the other time, expected value of Y would be equal to expected value of Y bar. Y bar here equal to P cap. We seek it to get the expected value of P cap. So expected value of P cap is going to be expected value of Y bar. And don't forget the expected value of Y bar equal expected value of Y. That's going to be P. Now, the next thing to do, don't forget, we'll be giving P to be 0.5, which means the expected value of P cap is 0.5. Now, we got the expected value of P cap. P cap is a random variable. Then we also need the variance of P cap. Okay, now how am I going to know the variance of P cap? I told you the other time, the variance of Y, if the variance of Y is sigma squared, the variance of Y bar is going to be variance of Y divided by N. Now, Y follow Bernoulli distribution. The variance of Y for Bernoulli distribution is 1 minus P. Now, I want to figure out the variance of Y bar. Okay, and the variance of Y bar is the variance of P cap, and that is actually going to be the variance of Y divided by N. So which is why I got P into 1 minus P divided by 100. Now we figure out the variance of P cap. Now the variance of P cap now equal P into 1 minus P divided by 100. Or what I'm just going to do is to plug in. What is the value of the N? Sample size. It's 100, right? And what is the value of P? That has been given 0.5. When I plug that in, this is what I'm going to get. Take a look at that. Any question? Or now I figured that out. Any question? Okay, so when you take a look at give me 1 second. But before moving to that, you know what I just did right now? Give me 1 second. Let me make it big so that you can be able to see it. Okay. Now, when you take a look at this guy, this is what I'm talking about. We just got this guy now. Um, okay, we just got this guy now. We got the variance of pickup. Okay, we got the variance of pickup, and we got the expected values of pickup. Okay, if I really want to conduct, who is that? Is somebody asking a question? Okay. Now, if I want to make an inference about pickup. If I want to make an inference about pickup, I actually need to get the mean of the pickup and the variance of the pickup. If I want to make an inference about a statistic can be mean, can be Y bar, can be pickup, can be difference of means, can be difference of proportions. But right now, I've already figured out the mean of pickup, the variance of pickup. Then I want to see if I will be able to use a central limit theorem. But because the sample size is more than the threshold is 30, and we got a sample size of 100, then I'm actually going to use the central limit theorem. Take a look at that. I'll be able to use Z. Don't forget the other time, the implication of central limit theorem is normality. And I told you normality facilitates standardization and Z-score. I told you the other time, right? Okay, now we're going to make use of a Z-score where we're going to have a pickup minus the mean of the pickup. The mean of the pickup is P, which is the expected value of the pickup that we've already obtained here. Then divided by the square root, which is going to be like divided by the standard deviation of pickup. The standard deviation of a pickup is the square root of the variance of a pickup. You know, we got in the variance of a pickup here, right? Then you're just going to find the square root. Take a look at that. Now, the central limit theorem can be applied because the sample size is at least 30. And that was why I said that will be approximately distributed normal with mean of 0 and the variance of 1. Now, what is the question? What did they ask you to do? We actually want to find the probability that the sum of electorates or voters that will support this candidate will be less or equal to 45. This is a probabilistic interpretation. Don't forget, what is the meaning of T? T is the sum. P cap is not a sum. P cap is a sample proportion, which is the ratio of the sum to the number of sample size. Now, I want to find the probability of sum less or equal to 45. If I want to do that, then I can go from T to P cap. If I want to go from T to P cap, I'm actually going to divide T by 100, and that will give me P cap. And I'm also going to divide 45 by 100. Then I'm now working with this guy. I'm now working with the probability of a P cap less or equal to 0.5. Now, all what I'm just going to do now is to plug in the values of a P cap in the expression, and then I'm going to use the statistical table. So now take a look. Oh my God. Take a look at this now. I've already plugged in the values of P cap. Don't forget there's a difference between a P cap and a P. Okay, and at the end of the day, we got a Z less or equal to -1. We can check that from statistical table. Okay, or for those of you that use R, it's going to be P norm of -1 in R. If you use statistical software R, and that will give you the 0.1. It's going to give you this guy here, okay, which is 0.159. If I want to get that in percentage, I'll multiply that by 100. That will be 15.9%. The 15.9% that we have here is the probability that a proportion of voters that will vote for this candidate will be 45% or less, which is the same thing as 45 people out of 100. But let me tell you this. Before going to calculate this probability, do you know that without normal approximation, before 1733, before De Moivre discovered normal approximation to binomial, what are they using then? You know what they were using? They were using the binomial distribution. And I'm going to go back now. Then why is it that we cannot? Why are we seeking for normal approximation? Why is it that we cannot work with binomial distribution? I'm going to tell you now. When the sample size is large, binomial distribution will be complicated. And let me tell you, I'm going to show you now. When I use binomial distribution without normal approximation, that is exactly what I'm doing here. Can you see that? Using binomial distribution, don't forget t is a binomial random variable, right? Okay, I want to find the probability of t less or equal to 45. I'm going to use a binomial formula. You know, binomial formula, n combination t, p raised to power t, 1 minus p raised to power n minus t. That is a binomial formula. Okay, now you can see I'm going to sum up from 0 to 45. Take a look at that, and the result is going to be 18.4%. Without approximation, the result is 18.4%. But that would be so tedious. Okay, but using normal approximation to binomial, okay, the results actually gave a different, we got a different result, which is uh oh, give me 1 second, which is so which is this guy. This is what we got, and sorry, this is what we got, and this is the actual probability. The right distribution with before the conversion will give you the true value. Okay, normal approximation will come with the error, and that is the reason why 15.9% is not the same as 18.4%. Approximation does not give an exact. Does that make sense? But because it's very close, there's no problem. We don't have any worry with that. Now, before I go into second material, we got a rule of thumb. When do we use a normal approximation to the binomial distribution? I told you the other time, we got to make use of sample size. When sample size is large, but we got a formula for that. Take a look at this. When the sample size is greater than 9, the maximum multiplied by the maximum of p and 1 minus p divided by the minimum of p and 1 minus p. If you want to figure out what the sample size is going to be, you need to be able to tell us what your p is. Okay? When your p, now example, when p equal to 0.3, when you plug in that, what is going to be the maximum? When p is 0.3, 1 minus p will be 0.7. What is the maximum between 0.3 and 0.7? That's going to be 0.7. That's why you got 0.7 in the numerator, and you have 0.3, which is the minimum in the denominator. Then, which means if I'm anticipating to estimate, if I'm working toward p equal to 0.3, I should be ready to take a sample size more than 21. That's what I mean. Any question before I go to the second material of the day? Any question? This is the normal approximation to binomial. This was given in 1733 by De Moivre's. De Moivre's. You say what? Why is it have to be 9? Okay, that's a very good question. We've done some kind of calculation with derivation, to be, for us to be able to put 9. Okay, so there's a kind of stuff that we put into play before we have we call it sample size determination. Okay. Okay, now I'm going to stop my share now. Go ahead. No, it's 9 times the maximum between p and 1 minus p. When p equal to 0.3, right? Okay, 1 minus p will be 0.7. What is the maximum between the two? 0.7. That maximum is going to be in the denominator, while the minimum is going to be, in the numerator, while the minimum is going to be in the numerator. So when you do the ratio of that, you multiply by 9. Then the sample size must be greater than whatever you get. Okay, I'm going to stop my share now. Then I'm going to share the second lecture material. Give me 1 second. Okay, so in the second lecture material, I call that application of central limit theorem. But let me tell you, even the first material is also an application of central limit theorem. Does that make sense? Okay, we just want to go further. Okay, we just want to go further. Okay, let me make it so because I want to be able to write. So, okay, now I want to move right now application of central limit theorem. Now, I want to have a review on the law of large number, review on the central limit theorem. Then I go into application, real world application of central limit theorem. But you know what? I've done all of this in the last class. Now, but for us to have a recap, between, the law of large number and the central limit theorem, because the two of them have a kind of connection. I'm going to say, of course, the law of large number just, tell us when the sample size is large, of course, the sample mean, okay, we converge to population mean. The sample proportion converge to population proportion within a certain threshold. Okay, when you say within a certain threshold, you're actually talking about weak law of large number. But if you are talking about convergence everywhere, for almost all outcome, then you talk about strong law. Now, why the law of large number talk about the convergence of sample statistic to population or true value. When sample size is large, then the central limit theorem, on the other hand, actually talk about convergence in distribution. Okay, regardless of the population distribution, when the sample size is large, the distribution of the statistic will convert to normal. And when it converges to normal, of course, uh, normal distribution facilitates standardization and z-score. And of course, in statistics, when we are conducting a test that assume normality assumption, of course, that will enable us to figure out how the p-value associated with the test, because z-score is going to be easy, just going to check the table, and every other thing that we want to do is actually, so that simplifies you know, computing probability value. Okay, so I actually want to move. Of course, I think I've a review on central limit theorem. Okay, now what I'm trying to show right now is the central limit theorem. Of course, we did this the other time. So, you can see as n tends to infinity, the UN converges to standard normal distribution. I told you normality facilitate standardization, okay? And that will make our work so easy. Okay, now I want to move. Okay, now take a look at this. We normally start with a skewed population. What do we mean by skewed population? A population, that is maybe most of the data fall to a particular side, whether to the right or to the left. That's what we call a skewed population. So a skewed population is not normal. This is not normal, okay? But you know what? Because working with a skewed population normally requires an extra statistical or mathematical effort. And we're looking for a way to simplify a situation. Working with normality assumption, if everything go okay, always make our work very, very easy. And that's why we want convergence to normal, of the distribution to normal. Take a look at what I'm going to do. Oh my God. Let's say we got a random variable y, that is skewed, whether skewed to the right or skewed to the left, provided we choose a sufficiently large sample, the distribution of the sample means we follow normal. You can see that. And, maybe we started with the income of individual may be skewed, okay? But when we actually do a sampling distribution where we do a repeated trial, okay, we allow simulation and we get a lot of sample means, then provided the sample size is large, of course, the distribution is going to be normal. And when the distribution of the sample mean is normal, or the distribution of sample proportion is normal, that will give us an opportunity to be able to use, we can find the probability associated with the sample mean, with the sample proportion using normal statistical table, because assumptions of normality, let me tell you this, central limit theorem facilitate normality under certain condition. Normality facilitates standardization and z-score. Does that make sense? Okay, now I want to move right now. Okay, now I what are the step-by-step implementation of central limit theorem in a real-life business problem? Let's say we have a company now, and we actually, maybe we're producing, and what we produce varies, maybe in number, in number, okay? And we actually want to know uh, what is the average. We want to get a true average. We want to figure out the true average. Number one is define the problem. What do I want to do? Oh, I want to know the amount, the average amount of the quantity that we produce in this company. Oh, or I want to know the average household income in a particular country, or or I want to know the average, the true average vaccine effect. Stuff like that. I want to know different kind of stuff. We're going to start by defining the problem. Then the next thing is to figure out the sample size. Okay, but you know that you know how to figure out the sample size. You know, by central limit theorem, we expect the sample size to be at least 30 if you're for working with the mean. Then we decide on the sample size. Then we're going to collect the data. When we collect the data, we calculate the sample mean. Then we repeat sampling. Why are we repeating sampling? We want to have several means. Does that make sense? Because you can't do sampling distribution without having several means. Several means is like you go into the population, you choose sample size, at so many occasions. In each occasion, you figure out the mean. Now, if you visit the population 1,000 times, you're actually going to have 1,000 means. Why are you doing that? You're actually doing that because having more than one mean will give you an opportunity to be able to know whether the distribution is normal or not. Does that make sense? Okay, so what you're going to do next, right? You calculate the means of the means. But let me tell you this. What do we call the means of the means? Oh my God. The means of the means is actually, give me 1 second, is what I call expected value of y bar. That is the mean of the means. Y by itself is a mean. Expectation is a mean. The mean of the means. If I go 1,000 means, then I'm going to get the mean of that. Does that make sense? Oh, what is the next? Then I'm also going to do the standard deviation of the mean. So which means I will first need to start with the variance of the mean. Then when I get the variance of the mean, the standard deviation of the mean is actually going to be the square root of the variance of the mean. Okay, the moment I go there, oh my God, I'm set. I'm set. I'm set. I'm set. Okay, the moment I get all of that, the next thing is to apply the CAT, apply the central limit theorem, and don't forget. So now that is the procedure. Any question? And I want to walk you through an example now of how central limit theorem work. You already see the procedure. Okay, now let's look at the example. So we want to talk about achievement test. Achievement test score of all high school seniors in a state have a mean of 60 and the variance of 64. Okay, you know what they give you here, right? That is expected value of y. If y represents score of individual, expected value of y equal to 60, the variance of y is 64. That's what you are giving right now. That is sample size 100. Now that you got a sample size of 100, now let's take a look at the question. Oh, give me 1 second. I'm gonna stop. Let me see. I'm gonna stop my share now. Give me 1 second. I was gonna stop my share. That's not gonna reflect. Yeah. Oh, give me 1 second. I'm gonna remove that guy. Okay. I'm gonna share that again. Oh, okay. So show me that. Oh, not this guy. That's a different one. See, okay. So if I share that one, let me see what's gonna play out. Okay, come on now. Okay. Ah, that's okay. Think I'm gonna see. So, uh, okay, come on now. Okay. Okay, so okay. Now a random sample of n equal to 100 students from one large high school at a mean of 50. This guy is a sample mean. 58 is a sample mean. You choose a random sample from a particular school, but in general, this guy here is a population mean. This guy here is a population variance. I needed to take note of that. Now the question now, is there evidence to suggest that this high school is inferior? You know, the high school where the 100 scores was choosing? We want to see. So which means we want to calculate the probability that the sample mean is at most 58. At most 58 means probability that sample mean is less or equal to 58. That is what we want to find. This is the same thing as testing hypothesis, where the hypothesis is going to be mu. The hypothesis is actually going to be mu equal to 60. Alternative. Who can tell me what alternative is going to be for extra credit? Go ahead. You're very close. You're also very close. Okay, this is what happened. Under the non-hypothesis, mu equal to 60. What is the meaning of inferior? Inferior is called less than. So the alternative will be mu less than 60. Does that make sense? When the non-hypothesis is mu equal to 60, alternative hypothesis will be mu less than 60, because what we want to find is there evidence to suggest that this high school is inferior in terms of, having an average less than the national average? That's what we mean. Okay, now we're gonna which means, is it possible that a 100 sample from this population has a sample mean at most 58? Now this is the interpretation. Okay, this is the interpretation. I need you to take a look at this guy now. Why IID, we can apply central limit theorem. What do we want to do? You see that? We want to find the probability of y bar less than or equal to 50, equal to 58. Then we're going to use the idea of a central limit theorem. The sample size here is at least 30. Okay, what does it mean? What is the mean giving? 60. Plug that in. What does the sample mean? 58. When you do that, that's what I'm doing here. Okay, that's exactly what I'm doing here. You see that? And at the end of the day, I got my z-score. My z-score was negative 2.5. I can check from statistical table what that value is. If you want to use if you're using R, that's going to be P norm of negative 2.5. What do we have now? That probability is 0.0062. You know the meaning? The probability that score from that population, which population? Population that have a mean score of 60. Okay? So the probability that, you're going to take a sample, the mean of score will be less than 58. It's actually very, very small. Do you know that in hypothesis testing that we're still going to do, in hypothesis testing, this is a p-value. And when a p-value is less than alpha is the level of significance, 0.05. When a p-value is less than the 0.05 level of significance, the null hypothesis is rejected, which means mu is less than 60. So what are we trying to say here? We're trying to say the probability that you're actually going to have a mean score less than 58 from a population with a mean score of 60 is that. What is the interpretation here? Because this probability is so small, it is unlikely that the sample from the school of interest can be regarded as a random sample from the population, which means that very school is in focus. They need to do more. They are doing very badly compared to maybe not. If that very 60 is a national average, does that make sense? That's exactly what we're trying to say. So the evidence suggests that the average score for this high school is lower than the overall average. That's what we mean. We've taken it. We've actually done statistical inference now. Now I want to move to another question. Go ahead. Yeah, the 0.05 is a level of standard level of significance. If the p-value is less than the standard level of significance, that actually indicating that you are rejecting the null hypothesis. Does that make sense? So, and if you want to look at it in probability value, this is so small, very, very small. Okay. Now, the service time for customers coming through a checkout counter in a retail store are independent random variable with mean 1.5 minutes, variance 1.0, approximate the probability that 100 customers can be served in less than 2 hours. Oh my God, I know the mean. The mean time the served customer is 1.5 minutes. We now want to figure out the probability that 100 customers will be served in less than 2 hours. Less than, less than 2 hours, but one customer is served, they have a mean of 1.5 minutes. If I can apply central limit theorem here because the sample size is large. Okay, so take a look at this. Y1 what to Yn follow a distribution. I have a mean of 1.5, and that, what do we want to do? We want to find the probability that sum. We don't only find probability of the average, we also find the probability of the sum. Summation Y less or equal to 120. I can convert that to the average by dividing by sample size. I'm actually going to divide all of them by sample size. If I do summation Y divided by N, that will be Y bar. If I do 120 divided by 100, that will be 1.2. Okay. Now which actually means finding this is the same thing as finding this. Now, and I know, I told you the other time, since I'm focusing on random variable Y bar, we need the mean of the Y bar. We need the variance of the Y bar. Expected value of Y bar is same as the value of Y, which is 1.5. I told you the other time. Then I need the variance right now. The variance of Y bar is the variance of Y over N. You're given the variance will be 1. The sample size is 100. The variance of Y bar will be 1 over 100. The standard deviation is going to be square root of that. Okay. And when you have square root of that, the standard deviation is going to be this. And of course, with that, you can actually use the central limit theorem approach where you're going to plug in. Now see, I've already plugged in. I got z to be -3. I can make it a statistical table. And at the end of the day, this is the result. The probability is also very, very small. Okay. Now we say the probability that 100 customers can be served in less than 2 hours is approximately that. This small probability indicates it is virtually impossible to serve 100 customers in only 2 hours. Does that make sense? Okay. Now, I want to move to another exercise. This is from the textbook. Okay, the exercise from textbook. Now, take a look at the exercise. I've been working with one population. What if I have two populations? I'm going to use S and Y. S is going to be random variable. Y is going to be random variable. S is going to have its mean and the variance. Y is also going to have its mean and the variance. And of course, the total number of sample size, maybe the sample size I choose in, for S is Sm, is M, and the one for Y is N. The totality of the sample size is going to be N plus N. Okay, imagine I want to compare the standard of living in two countries. Maybe I want to compare the average household income in the United States and Canada. Okay, take a look at this guy now. I'm actually going to get sample mean X bar, sample mean Y bar, and I'm going to find the difference between the two. Okay, if X bar is a random variable, Y bar is a random variable, the difference of a random variable is a random variable. Then I also need to I want to find what is the mean of the difference. What is the variance of the difference? Okay. Now, provided the sample size is extremely large, you know what? I'm going to stop here. I don't want to rush you before I start the next material. The material for next week, I'm actually going to start from here. What I want to talk about now is when I have two populations where I want to compare averages. I can work with two populations where I also want to compare the proportions. Okay. Now, right now, if I want to work with two populations where I took a sample size from population 1, I took a sample size from population 2, I compute the mean here, I compute the mean here, and I want to find the difference. The difference of the mean is also going to be a random variable where we also need to know the distribution for that. If I want to know the distribution, I need to find the expectation of the difference. I need to find the variance of the difference. So how do we do that? And how do we apply central limit theorem? I'm actually going to continue. I'm going to start this on Monday before I start, the material for Monday. Any question before I go today? Is your previous example? Okay. Why we don't have to mention what? Pick up? No, because we're not dealing with proportion. Proportion pickup is I'm talking about certain thing is sat in a whole. That is where we use election. In election, some people favor this candidate, some will not favor. That's a proportion. Or I figure I want to know the number of female in U.S. Congress. That's a proportion. But if I'm talking about average, like sum of something that will lead to average, then I'm going to be talking about Y bar. Do you understand? But let me tell you this. Y bar, P cap is the same thing as Y bar in the actual sense. But you can use P cap here. It has to be Y bar. Yeah. Any other question? Any other question? Okay. Make sure it's another weekend. Make sure you all stay safe. Have a lovely weekend. Bye for now, everyone.